When spreadsheets are not the right choice, you may choose a code-based tool with a programmable interface. For tokenomics, the greatest number of variety of tools are Python-based. But if designers and engineers are really familiar with other tools written in R or MATLAB, they can put those to work too. I'm mostly going to focus on the Python tools here, but I want to be upfront. I took my fair share of stats and econometrics up to master's level, but I have limited experience using data science and Python in my professional life so far. What I'm going to be sharing about these tools today mainly comes from the Token Engineering Academy. They're a great team and community, and if you want to do real digging in this area, I strongly urge you to take their courses and join up to their Discord channels to learn more from these experts directly. I provide links to their website and Discord channels below. All I'm doing here is giving you a cursory introduction as befits my current level of experience in these areas. So imagine you're starting off with a completely blank screen. Scary, right? What would the development of your tokenomic model look like in this environment? Well, it would follow a series of stages and could look something like this. First, you'd start off with your model specification. This is where you determine how many components your model has and how they relate and interact with each other. You do that using functional or mathematical relationships. You then have to decide how your simulation is going to run. This would involve you choosing outputs and KPIs for the simulation to generate and decide which input values need to be run through your model and in what way. You then move on to the evaluation of these outputs, where we would use statistics to summarize and interpret the outputs from our simulation. We could also consider how to use real-world data to evaluate our model's validity and or to run real data through the model itself after checking its integrity. We then move on to optimization, which may involve us making changes to parameters that are in our control in order to improve outcomes. You may also be making changes to the underlying structure, which in effect makes this loop right back round to the beginning again. To give you a sense of how these steps may play out in practice, we're going to sketch out how we would apply them to create a simulator for a simple automated market maker decentralized exchange. Again, this is just a very high-level digest of what you'll find in the Token Engineering Academy courses. So we start with our model specification, where we define the relevant components in our system, how they interact, and how they affect each other. It will generally be helpful to approach this by thinking of our system as having two broad groups of parts. First, we have the environmental features that create economic consequences for our agents. In this case, that's the AMM DEX itself. And then we have the agents that interact with it. Let's start with the DEX first. There are four possible actions we can take. We can add pairs of tokens to our liquidity pools. We can withdraw pairs of tokens from our liquidity pools. And we can swap token A for token B, or we can swap token B for token A. Both of these actions involve increasing the balance of one pool and decreasing the other. Next, we have the model of our agents. This includes the decision rules that the agents use to choose an action in the system, and perhaps we determine different kinds of agents that engage with specific parts of the system only or use different decision rules to each other. We also have assumptions about the occurrence of these types in our system and possibly add details about how these proportions of users change over time as well. Notice that since these decision rules reference the current state of the DEX, and since that state is the result of the prior agent's actions, this means that the agents are indirectly reacting to each other. And that means that if agents take more than one action, the action that B takes now affects the action that A decides to take later. This introduces feedback into our system. Okay, so pausing for a minute, at this point, we've specified the relationships between all the parts of our system and how they affect each other, and therefore how the state of the system overall changes upon different sorts of events. So the next big step to take is defining a simulation process that gives us insights about how the system behaves under different circumstances. It's at this stage that it becomes obvious why we can't model the system adequately in a spreadsheet environment. First, key events are not centrally coordinated. Each of these actions may be taken by independent agents, each acting in their own interests. Next to note is that the possible combination of events is very large. Not only do we have 4 categories of events, but each of those can differ continuously in their magnitude according to some probability distribution. They can be larger or smaller swaps, and we can add more or fewer tokens to the liquidity pools. But the real clincher is that the agent decision rules introduce feedback into this system. Agent choices are affected by their own earlier actions and the earlier actions of others. This means that the sequences of events matter. Certain behaviors or outcomes may only appear when other foregoing events have occurred. We say that these events are path-dependent. These path-dependent events may include ones that we might classify as a failure of some kind relative to the goals and objectives we have for this system. In these cases, we can't limit our analysis to a small number of boundary cases. This is what we would typically do in break-even style analysis that we commonly perform in spreadsheet modeling. Recall how we illustrated this idea earlier. In simpler systems, we can just reduce the cases of interest to a few manageable edge cases, like you see here. But if feedback and decentralization occur, this means that failures may occur non-trivially inside that space. So that vastly increases the space of events that we need to search and test. And that means that a thorough evaluation of our system requires us to explore that large event space in detail. This means that it's likely we'll need to run an arbitrarily large number of iterations for our simulation. This is something that is not easy to do in a cell-bound spreadsheet framework, and furthermore, we want to be able to do that as quickly as possible. So it's better for us to get rid of all the processing overhead that's tied up with a spreadsheet's visual environment. To actually specify the simulation process, we need to think about our inputs, outputs, how we structure these data to generate a comprehensive record that we can efficiently and informatively analyze when the simulation is done, and perhaps how we structure these data variables to be processed efficiently by the simulation process. We also need to give some thought about how we select input values to pass through our model and whether this makes sense, if it's realistic, or whether it's efficient. The next step is to evaluate the output of our simulations. We may first need to test the validity of the model itself by running input values through it that generate known results that we can use to check its behavior. If that goes well, then we can start paying attention to what the model is actually telling us, using appropriate descriptive statistics that summarize and compare large volumes of output data. And we can also use statistical tests of significance to determine how much weight we lend to any conclusions and also create helpful visualizations for our data. In practice, the design of these evaluations will probably take place in tandem with the design of the simulation process itself. We may then move on to thinking about how we make use of real-world data. We may do that to create further validation of our model by comparing the model simulation output to real-world measurement data, or perhaps we try driving the model with the real-world data directly, or else use real-world data to define appropriate sampling distributions for the events that drive our simulations. Finally, we get to optimization. We may change our model structurally by adding new agents, rules, or processes, or tweak arbitrary parameter values that are in our control. Python has several optimization libraries available to help us tweak these values to achieve some desired criteria. Again, all of these recent steps are definitely not suitable to handle in spreadsheet environments. Now, if that sounds like a lot to set up for each and every modeling project, well, to some extent, it is. You may decide that you're comfortable with that, but if you're not, Block Science is developing an exciting Python-based tool called cadCAD. That stands for Complex Adaptive Dynamics Computer-Aided Design. cadCAD leverages general frameworks that we use to analyze and describe complex adaptive systems. They use these to create reusable functional containers and simulation patterns that help us structure the modeling, simulation, and evaluation of these systems without having to redo so much work each and every time. cadCAD is also coming up with convenient ways to integrate real-world empirical data into the whole process. They offer their own set of training courses that are well worth a look in, and I provide links to them below. Finally, I think it's also worth highlighting another simulation package called TokenSpice, released by Trent McConaughey of Ocean Protocol. He's also been involved with the Token Engineering Academy as well. TokenSpice is also Python-based, but its distinguishing feature that I find pretty exciting is that it allows you to include Solidity smart contract code directly into the simulator loop, which lowers the risk of mistranslating the way your smart contracts behave in your model, and vice versa. Note that this feature for the time being is limited to Solidity, which is Ethereum's smart contract coding language, and therefore it's limited to the Ethereum virtual machine. This is a really cool idea, and I wouldn't be surprised if that kind of emulation becomes standard in all simulator packages at some point in the future as an important and valuable means of mitigating modeling risk. So all of this looks tremendously impressive, but are there any risks or drawbacks to this modeling approach? Well, I think there are, not so much with the approach in general, which I think is equipped to handle pretty much anything, but in terms of how these techniques are used and conducted. First of all, there's a danger of becoming too wrapped up in modeling that is purely theoretical. As the saying goes, all models are wrong, but some are useful. We could continue adding elements to our model, optimizing them, and think that we're doing a great job covering all the possibilities and eventualities. But if we don't cross-reference the model with some real-world data as soon as possible, our modeling may be headed in the wrong direction, or we may just be doing work that just doesn't give us a payoff in terms of our decision-making. Another related risk is that we're not being practical in the way we design this. And this refers to the second part of that earlier saying, we need to make sure that this model is useful. This may not happen if we are caught up in trying to make something that is obsessively trying to match up our view of what we think is going on in the real world. This can give us a model that is too complex to guide decision-making or to offer clear and effective guidance. If you have a bazillion parameters that all interact and affect each other, that can really muddy what the effective course of action needs to be in a given situation. I should point out that this is a trap that any kind of modeler can fall into, and it's certainly one I have stumbled over lots of times earlier on in my career. The next thing to notice is that this approach requires us to specify everything that we wish to include in our model and encourage us to define that structure right down to the agent level. But in practice, it may not be possible to do this in ways that are useful. There may be too many behaviors to track or too many new types and strategies that are emerging in a really fluid and unpredictable way. In these situations, it may be more practical to identify aggregate measures that drive KPI values, and then we can either reformulate our causal model in terms of those higher level parameters, or else use machine learning techniques to help identify the relationships with our key outputs and use those to create alternative systems to regulate our system. The next issue I want to highlight is just how technical this toolset is. This can create problematic disconnects with the executive stakeholders who may not be able to engage with the model's development or else demand that this development be rushed in some way without understanding the risks involved. In addition to that, if the modeling sits in the hands of just one expert, this can create substantial modeling risk for your project. You may be able to mitigate these risks with strong testing or quality control processes, or by having more than one person contributing to the development, or else maybe having recourse to some kind of independent third-party audit. But all of these options are going to involve some of the most expensive talent to hire in the market, so that creates other frictions for enterprises who may just be getting started with their designs. The final important point we need to consider is that modeling experts may fail to situate the model's calibration within the larger business context that ultimately decides the success of the project. It won't always be appropriate to ask your Python modeling expert to have an understanding of financial accounting and business administration. So in these cases, it may be necessary to collaborate with business modeling or financial modeling experts that do have that domain expertise so that the model can be optimized and situated in a complete business context. So, wrapping up, this is an incredibly powerful toolset, but one that still needs to be used carefully and with awareness of the potential pitfalls. This kind of modeling may be best suited to systems that are complex due to the agent independence and feedback that create this larger parameter space that we need to explore and evaluate. But perhaps these tools and methods start becoming less valuable when the systems we need to model are just so open and complex that formal specification becomes either a vanity project or a fool's errand at best. In such cases, we may tilt towards greater reliance on inferential methods to identify key dependencies in our system for us and to monitor and manage our system using these. If all of this still seems super daunting to handle, don't worry. That doesn't necessarily exclude you from simulation-based modeling, because there is another simulator tool that we have available to use which leverages our visual cognition to do this work while still admitting far greater modeling flexibility and capability than spreadsheets offer.